Okay, let's continue with section 15.3. So recall what we're doing. Okay, so a review, small review. We say f is conservative or path independent if and only if for all a, b in the domain integral c of f dot dr is the same for all path c from a to b. And then we prove the loop test, which was good to check if something is conservative or not, which is a good negative test. It's good to use it to prove that something is not conservative. Then the loop test says f is conservative if and only if integral over c of f dot dr equals 0 for all c loop. And then we proved the fundamental theorem of line integral, which says integral over c of f dot d of grad f dot dr, where c is a path from a to b, this is equal f of b minus f of a. And this implies, as a corollary, that if f is a gradient field, then f is conservative. And then I told you that the reverse is also true. No pen path connected domain. So now to prove that something is conservative, we have to go and see if it is a gradient field or not. So this is our goal. So let's do some motivation for the remaining of the lecture. Let's say f is conservative. Then if f is conservative, this implies that f, which is equal m and p, equal grad f. Because conservative from the above theorem implies that it's a gradient field for some function f. Now assume, for technicality issue, and we'll tell you why, assume that m and p have continuous first order partial derivatives. Okay, so I put this into parentheses. This is not a theorem, just a motivation. Now let's say big F equal grad little f. So we have fx equal m, fy equal n, and fz equal p, if big F is conservative. But this implies that fxy equal my, fxz equal mz. Similarly, fyx equal nx, and fyz equal nz, and fzx equal px, and fzy equal py. But by the mixed derivative theorem, and this is why I need the partial derivative to be continuous, mixed derivative theorem, we have fxy should be equal to fyx, and fxz should be equal to fzx, and fyz should be equal to fzy. Then the conclusion: if f is conservative, I have my is equal to nx, mz should be equal to px, and nz is equal to py. This is if f, because this is fxy, is fyx, fxz and fzx, and fyz and fzy. So if a field is conservative, then my should be equal to nx, mz equal to px, and mz equal to py. And if you remember the following field, we proved that the following field is not conservative, which was the field f equal y I plus x squared j. In this case, I only have m is y, and n is x squared. Notice that mx equal my equal 1 and nx equal 2x. These are different than not conservative. Because we have that if it's conservative, these components should be equal. But now the question is, and this is a big question, is the converse true? And the answer is, in general, it's not. And let's go back to our example. Recall that f of xy, which is equal minus y over x squared plus y squared I, plus x over x squared plus y squared j. Recall that this is not conservative, because we showed that since integral over x squared plus y squared equal 1 of f dotted with dr, this is equal minus 2 pi, which is different than 1. However, I have m sub y, which is minus y over x squared plus y squared sub y. This is equal, let's put the minus outside, x squared plus y squared squared is equal 1 times x squared plus y squared minus 2y times y. So this is equal minus x squared minus y squared over x squared plus y squared squared. Okay, let's check. So yes, this is my 1, 2y, x squared, y squared. So m sub y equal y squared minus x squared over x squared plus y squared squared. And n sub x, which is x over x squared plus y squared sub x, this is equal 1 times x squared plus y squared minus 2x times x over x squared plus y squared squared, and this is equal y squared minus x squared over x squared plus y squared squared. So this implies that f satisfies the component test, but f, as shown with the loop test, is not conservative. So the converse is not true. Okay, this f is not conservative in R2 minus 0, 0. This is important. So in this domain, f is not conservative. And we're going to see now a condition that will make the converse correct, and we'll explain why in this case the converse did not work. So definition, we say that a domain D is simply connected if and only if every closed curve can be deformed continuously into a point without leaving D. And this is, this is not a very rigorous definition because we need more components to make it rigorous, but let's give an example. So a first example, let's take the whole domain. Let's take R2. Is it, so this is the whole thing. Now, is this simply connected? Yes, I take any curve, and notice that I can shrink this curve. I can shrink this curve until it's a point without leaving my domain. What if I take the square with two border removed? Is it simply connected? And the question is also yes. The answer is also yes. If I have any curve inside D, I can shrink it until it reaches a point without leaving the domain. What about this domain? Is it simply connected? And again, here's the answer. So yes, yes, yes. Again, here the answer is yes. Because I can take any curve here. I should start with a curve in the domain. So I cannot take a curve that intersects the x-axis or a curve here. I can always shrink this curve until it reaches a point. I can shrink this curve until it reaches a point. Now, what about the domain that was a trouble in this example? So what about R2 minus 0, 0? Is this simply connected? And the answer here is no. It's not simply connected. Why not? Because if I take this curve, I cannot shrink this curve in a way to not leave the domain, because whatever I do, even I can try to move it to the right, move it upward, but wherever I move it, I will always end up intersecting the origin while I shrink it, or if I move it. So this is why this domain is not simply connected, because you cannot shrink this loop that I drew here into a point without leaving the curve. At some point, you will have to intersect the origin. Another example, R3. By the way, I will post a video from MIT that is a recitation only about simply connected domain. It's not the subject of the course, simply connected domain, but they come up here and they are important domains. I mean, this example that I did should be enough, but I mean, if you want to see more example, I can post this short video. So what about R3 minus 0, 0? Is this simply connected? Now you might think that this is the same as R2 minus 0, 0, because let's start with a disk like this that contains the origin inside. Can I shrink this curve without leaving the domain? And the answer here is yes, because I can move upward. So I take this piece of loop and I move it upward, and then it becomes like this. And then I can shrink it until I reach a point. So this is, yes, simply connected. What about R3 minus the z-axis? So I remove an axis and then I take. Now, is this simply connected? You should know that the answer is no. Why? Because if I take this loop around the z-axis, whatever I do with this loop, move it upward, downward, shrink it, I cannot reduce it to a point without leaving my domain. So this is some example of simply connected domain. And then I have the theorem that says the following. Let D be an open, simply connected domain, and F equal M and P having with component having continuous first order partial derivatives. Then we have F is conservative. We know from before that this implied that my equal nx, mz equal px, and nz equal py. But the new thing here is that this is if and only if. So it's enough to check the component to prove that a field is conservative in a simply connected domain. Okay. So an example, show that f of x, y, z, which is equal y plus 1i plus x plus y z squared j plus y squared z plus z squared k is conservative. This is a previous exam, I guess. Then calculate integral over c of f dotted with dr with r of t equal arctan of t squared t4 plus 1 where 0 smaller than t smaller than 1. So that's a long exercise, but notice, okay, so solution. This one, I mean, where you appreciate the theorem, fundamental theorem of line integral, because you see that if you want to calculate this integral, then I will have to parameterize, which is this parameterization, and I have to calculate v of t and do the product between f and dot v of t, and this will be a long process. I mean, even now the process when solving it is not very short, but at least it's still shorter, let's say, and more efficient. So I have f, which is equal m and p, and I have m equal y plus 1, n equal x plus y z squared, and p equal y squared z plus z squared. Now notice that m and p have continuous first order derivatives. So they are nice function in R3, which is simply connected. So I can use the component test to prove, well, to prove that it's a conservative field. So let's see. So what is my? It's 1. What is mz? It is 0. What about an x? It is yz squared. Notice, n is the second component, so I calculate partial derivative with respect to x and respect to z. M is the first component, so I calculate the derivative with respect to y and with respect to z. What about n sub z? N sub z is 2yz. What about p? P is y squared z plus z squared. So, sorry, what is p sub x? This is 0. What about p sub y? This is 2yz. So notice that my equal an x, and this is doesn't look like this because I calculate an x wrong. N is x plus yz squared, so an x is 1. So my equal an x is 1. It's good to check. And mz equal px equals 0, and nz equal py equal 2yz. And this implies, since RC is simply connected, the component tests are satisfied, and this implies that f is conservative. Now, how do I calculate integral over c f dot dr? I have to use the fundamental theorem of line integral. So first, we find the potential or a potential function f such that a potential function little f such that big F is grad little f, i.e. I need f such that fx, fy, fz equal m and p. And there's somehow a process to do this. So I want fx to be equal to m. And what is m? M is y plus 1. So I want fx to be equal to y plus 1. But this implies that f of x, y, z, now integrate with respect to x. This is like a constant with respect to x. So you get xy plus x plus some constant that does not depend on x, but it might depend on y and z. So this will be plus some function of y and z. Now, if this is my f, what is f sub y? F sub y, differentiate the thing with respect to y. You will get x, the derivative of xy with respect to y is x. The derivative of x with respect to y is 0 plus g sub y. And I want this to be equal to n. And what is n? N is x plus yz squared. So this implies that g sub y of yz equal yz squared, which implies that g of yz equal y squared z squared over 2 plus a constant that doesn't depend on y. So it might depend on z. So plus a function of z. So this implies again that f of x, y, z equal xy plus x plus y squared z squared over 2 plus h prime, well, plus h of z. Now still one step, I want f sub z. So what is f sub z? Differentiate this, you will get 2y squared z over 2, and the 2 will cancel out, plus h prime of z. And this should be equal to p. And p is y squared z plus z squared. And this is p. Now this implies that h prime of z equal z squared. So h of z equals z cubed over 3 plus constant. You will always have a constant floating at the end because there's infinitely many potential functions that differ by a constant. So choosing c to be 0, we get that f of x, y, z, which is equal xy plus x plus y squared z squared over 2 plus z cubed over 3 plus a constant that I chose to be 0. You can choose it to be 1, you can choose it to be whatever you want, is a potential function. This means f equal grad f. So now I have to use so by the fundamental theorem of line integral. Remember, I have c is r of t equal arc tangent of t squared, t4 plus 1. So integral over c of f dotted dr equal integral over c of grad f dotted with tr, and here I had t between 0 and 1. And by the fundamental theorem of line integral, this is equal f of the last point, which is r of 1, minus f of r of 0. But what is r of 1? It's f of arctangent of 1, which is pi over 4. R of 1 here, this is 1 squared, and 1 power 4 plus 1, 2. What about r of 0? It's f of, what is arctangent of 0? It is 0. 0 squared is 0. 0 power 4 plus 1 is 1. And now I have f. This is f. So it's x, y, which is pi over 4, plus x, plus pi over 4, plus y squared z squared, which is 4 over 2, plus 8 over 3, minus f of 0, 0, 1. I replace x, y, this will cancel, this will cancel, this will cancel. So I will have minus 1/3. And this equal pi over 2 plus 2 plus 7 over 3, which is pi over 2 plus 13 over 3. And this is how we solve all these kind of questions. I have one more remark to say. So definition, something related to the differential form representation of a vector field. So we say that the form mdx plus ndy plus pdz is exact if and only if the field f equal mnp is a gradient field. Okay. One fast example. So example by showing that the integrand is an exact form, calculate integral 509 till 1 pi 0. Remember, this means it's any path between 509 and 1 pi 0 of 2x cosine y plus yz dx plus xz minus x squared sine y dy plus xy dz. So this is my form. I want to prove that it's my form. In this case, this is m, this is n, this is p. So I have to prove that m and p, so I should prove that m and p is a gradient field. But I have m and p have continuous partial derivative in R3. I have no problem at any point. So this implies that I can use a component test, which is simply connected. And what is m sub y? M sub y, differential respect to y, you get minus 2x sine y plus z. What about m sub z? M sub z is equal to y, because derivative of yz. What about n sub x? N sub x is z minus 2x sine y. What about n sub z? Is equal to x. Now what about p sub x? This is equal to y. And what about p sub y? This is equal to x. So this implies that m sub y equal n sub x, which is equal z minus 2x sine y. M sub z equal p sub x, which is equal to y. And n sub z equal p sub y, which is equal to x. So by the component test or the curl test, by the component test, also called curl test, m dx plus n dy plus p dz is conservative, is an exact form. Okay. Now next, so to calculate the integral, we find little f such that grad f equal m n p. Again, so I want f sub x to be equal to 2x cosine y plus yz. You don't have to start by f sub x every time. Sometimes it's easier to start by f sub y. And I put a lot of exercise in the problem set like this. Okay? So if f sub x is this implies that f of xy, this is m. So integrate respect to x, the integral of 2x cosine y, remember cosine y is just a constant respect to x. So this is x squared cosine y plus xyz plus some function that depends on y and z only. So next, we do f sub y. This is minus x squared sine y plus xz plus g sub y. And this should be equal to n. And n is xz minus x squared sine y. So this implies that g sub y at yz is equal to 0, which means g does not depend on y. So g of yz is some function of z. Again, this implies that f of x, y, sorry, here is a z equal x squared cosine y plus xyz plus h of z. So next, f sub z equal differential respect to z, this is a constant in z, this is xy plus h prime of z, and this should be equal to p, which is equal xy. So this means h prime of z equals 0, so h of z is a constant. When we finish by the constant, we can say choosing c to be 0, we conclude that f of x, y, z, again you can choose any constant, which is equal to x squared cosine y plus x, y, z, is a potential function to m and p. And therefore, by the fundamental theorem of line integral over, well, it was an integral from where to where? 509 to 1 pi 0, 509 to 1 pi 0 of m dx plus n dy plus p dz. This is equal little f at 1 pi 0 minus little f at 509. But this is f, so this means this is x squared, so 1 squared cosine pi plus 0 minus x squared, which is 5 squared cosine 0 plus 0, and this implies minus 1 minus 25, and this is equal minus 26. Okay. I will stop here, although I still have to do one exercise emphasizing the thing about simply connected domain, and this is something that we used to do in the recitation, so I will not do it now, maybe I'll do it next time. Okay, so study these things. You are now ready to finish all the examples and 15.3 also. I mean, there's this still small thing that I need to explain, but it's not much emphasized in the exercise in the book, but I might need it later, and it's a very important, idea, very interesting idea that I still need to do. Okay, thank you. I think that's, we conclude now then our first week, and please don't hesitate to contact me if you have any question. We are going to meet on Monday, and remember that on Monday you have a quiz. I will send you all the information about the quiz shortly. Okay, take care.